Look at the YouTube mobile homepage. Behind this straightforward grid of thumbnails and titles operates one of the most sophisticated industrial recommendation systems in existence. Recommending videos to billions of users from an expanding corpus of millions of items introduces the first major constraint: scale. Standard recommendation algorithms, like matrix factorization, map users and items to a shared latent space to predict interactions. These methods collapse mathematically when applied to a dataset of this magnitude. The second constraint is freshness. YouTube must constantly balance the exploitation of well-established historical videos with the requirement to instantly surface viral, newly uploaded content. The third constraint is noise. The system rarely receives explicit ground truth signals of user satisfaction, like survey responses or ratings. Instead, it must model highly noisy implicit feedback, relying primarily on user watch history to infer preference. To navigate the triple constraint without severe latency bottlenecks, YouTube replaced traditional matrix factorization with a two-stage deep learning architecture. The central engineering tension is strict, scoring millions of items for billions of users with a serving latency of tens of milliseconds is computationally impossible for a single model. This diagram illustrates the solution: a two-stage asymmetric funnel. The first stage is candidate generation. Its job is high recall, winnowing the entire corpus from millions of videos down to a few hundred broadly relevant candidates based on the user's collaborative filtering data. The second stage is ranking. Because the candidate pool is now strictly limited, this high-precision model can assign a highly calibrated score to each of the surviving hundreds of videos, determining their exact sequential placement on the user interface. This decoupled design allows YouTube to evaluate massive corpora offline while maintaining lightning-fast, highly personalized rendering directly on the user's device. Generating candidates requires solving an extreme multi-class classification problem. The network must accurately predict a specific video watch, denoted as W sub t at time t, choosing from millions of possible video classes. This graph shows how the network ingests data. The user's watch history and search queries are tokenized and mapped into dense vector representations, known as embeddings. An embedding is a mapping of sparse discrete entities into a continuous dense vector space. These individual embeddings are then averaged together to create a fixed-width input layer. These averaged vectors are concatenated with demographic priors, such as the user's age, gender, and geographic region. This combined data is fed through successive layers of fully connected rectified linear units, or ReLUs. A ReLU is an activation function that outputs the input directly if it is positive, and otherwise outputs 0, allowing the network to model complex, nonlinear interactions. The mathematical bottleneck occurs at the output layer. Computing a traditional softmax across millions of discrete classes takes far too long during training and serving. A softmax is a function that normalizes a vector of numbers into a probability distribution. The engineering workaround uses negative candidate sampling during training, where the model evaluates the true label against only a few thousand random negative classes. At serving time, the problem is reduced to an approximate nearest neighbor search in the dot product space, entirely bypassing the full softmax calculation. The candidate generation model intentionally sacrifices absolute precision for computational velocity, returning a rough neighborhood of relevant content that the downstream ranking model can refine. A deep neural network at scale will fail if you define the wrong surrogate learning problem. A surrogate learning problem is a proxy task the model is trained on, under the assumption that succeeding at this proxy will lead to success in the actual desired outcome. If given the opportunity, the network will exploit the structure of the site rather than learn true user preferences. Consider search query leakage. If the model knows a user just issued a search query for Taylor Swift, and the proxy task predicts the next watched video, the network simply predicts the videos appearing on the Taylor Swift search results page. This timeline shows the traditional collaborative filtering approach, holding out a random watch from the user's history and trying to predict it using the surrounding data. This leaks information from the future backward into the past. Predicting backward breaks natural consumption patterns, like discovering a hit song before exploring niche CACs. To solve this, YouTube uses a rollback method. The model predicts the next future watch, evaluating only the actions taken strictly prior to the held-out label watch. Discarding sequence information and strictly predicting future behavior forces the model to learn authentic human discovery patterns rather than optimizing for redundant site navigation. Machine learning systems trained to predict future behavior from historical examples develop an implicit bias toward the past. This makes it exceptionally difficult for the network to surface newly uploaded, highly viral content. Without correction, the multinomial distribution output by the recommender will merely reflect the average watch likelihood over a multi-week training window, effectively burying recent uploads. This graph shows the empirical distribution of a video's popularity over time. Engineers corrected historical bias by injecting the exact age of the training example directly into the network. This accurately maps time-dependent popularity. At inference time, when serving recommendations, this example age feature is explicitly set to 0. By forcing the model to operate as if it is always predicting at the very edge of the training window, YouTube solved the freshness constraint. With the candidate pool narrowed from millions to a few hundred, the system transitions to the ranking stage. It can now afford to compute highly complex features to finalize the presentation on the user interface. The ranking network uses continuous features describing a user's specific history with an item. It tracks past impressions to mathematically demote ignored videos. However, unlike decision trees, these deep neural networks are highly sensitive to the scaling of raw numerical inputs. Proper normalization of these continuous features is critical for convergence. The raw feature is scaled using cumulative distribution interpolation so that the values are uniformly distributed between 0 and 1. Along with the raw normalized feature, the engineers input the square and the square root of that value. Feeding these powers gives the network the expressive capacity to easily form super and sublinear functions of the feature. Architectural depth is irrelevant without precise feature engineering. The specific mathematical shaping of the data before it enters the hidden layers dictates final model accuracy. The final challenge is the output layer objective. Ranking purely by click-through rate optimizes for deceptive clickbait that users abandon. The network was re-engineered to predict expected watch time per impression, capturing genuine user engagement rather than superficial clicks. They achieved this using weighted logistic regression. In the cross-entropy loss function, the negative, unclicked impressions receive a standard unit weight of 1. This equation demonstrates the modification. The positive, clicked impressions are weighted by the actual, observed watch time of the video, denoted as T sub I. Assuming the fraction of positive impressions is small, the learned odds generated by this equation closely approximate the expected watch time. During serving, a standard exponential function translates this into the exact numerical score for UI ranking. By weighting the training examples within the loss function itself, the engineers mathematically filtered out clickbait without altering the underlying topology of the neural network. At this scale, the system's success is a product of specific architectural interventions, rather than raw model depth or compute power. The actual intelligence of the system relies on domain-specific engineering solutions. Asymmetric next watch prediction, example age injection, and watch time weighting are the specific structural hacks that make the theoretical math viable in production. These algorithms do not exist in a vacuum. They interact with the realities of human psychology, accounting for natural discovery patterns, viewer fatigue, and an innate attraction to novelty. At an industrial scale, the true art of deep learning lies in the counterintuitive ways you define your surrogate problem and align mathematical loss function with human behavior.